Thank you. So the next on the list is, the title is Full Chain In Situ Calibration of Hydroacoustic Hydrophone Stations. Please.
So, dear chairs, dear participants, thank you and good afternoon. My name is Ch2. I am the head of hydroacoustic team in engineering and development section at CTBTO. So that work was conducted together with my colleagues from our team, Mario Zampoli and Dirk Metz. Thanks for their support, and also thanks for my management for their support. So the content of this presentation, actually, I will talk briefly about the full chain calibration, in-situ calibration methodology for hydroacoustic hydrophone station. So that actually is a feasibility the feasibility of this initiative is currently being studied. So there is no commitment to that methodology. So internally we are working on that technically to make that happen for our hydrophone station. So this is a general picture that we already know. So in this slide you see the map of IMS network, and each pin represents the IMS station. So in total 337 stations are facilitating, and 90% around of these stations are built, and they are sending data to Vienna. And in total, there are 11 hydroacoustic stations, and these are detecting the pressure variation in water, and then capture signals transmitted across the long distances in ocean. That is something I think most of the people in here familiar about. So it's hydroacoustic network has 6 hydrophone stations. They are made up of bottom Moore triplet deployed at SOFAR channel, and they are sensitive to acoustic pressure variations in oceans. And beside these hydrophone stations, we have also 5 T-phase stations. They are land-based seismometers, which are more sensitive to ground vibration and detects hydroacoustic waves transmitted through the earth crush. And on the right side, you see the image, the schematics of a hydrophone station. So from the shore to the offshore, we have the shore facility that keeps the electronics. And from there, we have the trunk cable that connects the shore facility to the hydrophones. And we have 3 hydrophones, as you know. And at the first hydrophone, we have the electronics that converts the analog signal into digital. So at the moment, I will explain it in more detail, but at the moment, the only capability that the hydrophone stations are just the calibration of the electronics. So the hydrophone, the analog part of the station are not considered at the moment. So that is something, therefore, we would like to want to have an in-situ calibration to consider those effects as well. So in this slide, you see the details of calibration effort before and after deployment. So prior to the deployment, so an extensive and inclusive full chain system level calibration at operational depth and temperature in the laboratory environment are done. The hydrophone and the preamplifiers are tested in low frequency test facilities, while the digitizers are tested in a laboratory environment using simulated inputs. But once the system deployed, so once it goes underwater, the underwater segment digitizer electronics calibration is performed from the CRF. So that means that the contribution of the analog part do not consider in the calibration. And this analog part contains the hydrophone, the riser cable, and the preamplifier, which is very critical from our perspective. And this is how the calibration is done after the deployment. So from the CRF, a signal is sent to the electronic bottle, and it's a different type of signals, a continuous signal that we triggered from the CRF, and the electronic response is captured and compared with the nominal response of the system that was initially calibrated during the fabric acceptance test. So you see in here, the hydrophone and the preamplifier are not considered in this chain. So why the full chain in-situ calibration is important? So the hydrophone is actually the primary sensing element, and its acoustic performance is critical. And hydrophone performance may be affected by the external influences. And the analog part of the system may degrade over time, and the potential degradation is currently not accounted for in the system's traceability. This is a significant concern as CTBTO aims to keep the station operational well beyond their original design life until it fails. So therefore, we have to have knowledge about the analog part of the station as well. Full chain in-situ calibration would also allow us the assessment of the station health more accurately, thereby supporting sustainability planning and ensuring long-term reliability. And also it would serve as a key measure to ensure performance consistency and maintain the continued effectiveness of the hydroacoustic network. So I just would like to briefly give some examples from the recent, not recent, but past studies. So in early 1990s and 2000s, there are a couple of experiments to check the full chain acoustic response of the some stations. So that happened in 1999 on the left at Ascension Island, and seismic air guns were deployed to produce acoustic pulses. And these pulses were recorded by a calibrated hydrophone and compared with the station's hydrophone. So this method was promising, but the implementation is not so easy because the direct acoustic arrivals were contaminated by the strong seabed reflections, as the hydrophones in this case were positioned close to the ocean floor and the air guns were just below the seawater. Another study was carried on 2000. Instead of air guns, imploding spheres, glass spheres were investigated as an alternative to air guns. And the problem in the issue in this exercise was the spheres has a frequency response from 200 Hertz up to 800 Hertz, which is not the frequency bands of the PTS. So I'm not going to go into that detail, but there's a couple of calibration standards available. So IEC 60565 is one of them, and it describes the methodologies for the calibration in laboratories. But that standards defined primary and secondary calibration methods across a wide frequency range. And that standards can be used as a baseline for in-situ calibration, and the in-situ calibration can be built according to this understanding. So these are the documents that we considered at the moment during our assessment. And from those standards, I just would like to give some highlights about the methodology. So there are two types of calibration. that can be done on the field. So first one can be a hydrophone calibration using a calibrated projector. So in here, the projector emits a sound into the water, and by knowing the physical properties, I mean the calibration chart of the projector, you can calculate the sensitivity of the hydrophone. But in here, you have to know the distance in between the projector and the hydrophone very accurately, because this, in the formula on the right side, you see D is the distance, and due to the ocean conditions, the change in the distance may affect the result. And the challenge in here is that the frequency range of the PTS is very low, and this is something that we will discuss tomorrow in the meteorology session. But the calibration of the projector at those frequencies are very challenging, and there are actually a couple of NMIs, National Meteorology Institutes, can do this, and this is something needs to be spread out around the world. The second method is, instead of using a calibrated projector, a calibrated hydrophone can be used instead. And in here, you have to have, again, a projector that emits the sound. But by knowing the sensitivity of the hydrophone, you can compare the reference hydrophone with the hydrophone that you want to calibrate. In here,
Can we ask you to...
Yeah. Okay. So the most challenging part in here that you have to have two platforms, so that increase the financial burdens. So before I jump into the conclusion, so the key challenges are the calibration of the equipment, availability and meteorological traceability of the projectors and hydrophones are limited. So due to the low frequency, the number of oscillations at the hydrophone side without any overlap due to the reflections requires the use of signal processing techniques to reconstruct the signal sufficiently long to determine the signal's amplitude and phase. So this is especially challenging below 20 hertz, I can say. Deep water is one of the big challenges because you have to deploy your equipment up to 1,400 meters to reach the SOFAR channel. At the moment, there are no standard calibration procedures for Ch2 that consider the deep ocean environments. So accurate knowledge of the coordinates of the hydrophone is essential if you want to use the second methodology, comparing with a reference. Open ocean ambient and propagation conditions needs to be well defined, and the remote location gives lots of challenges and costs. So what is the future action in here? So we would like to work on the feasibility and the preparation. So we are very open to cooperate and make a joint work together with the institutions who has offshore marine engineers, and we would like to contribute, we would like to ask their contribution for the calibration effort and provide logistical support at remote stations. And we also get their support for addressing station-specific permitting issue. Exploring of the equipment is something that we need to work on, and we need to also work on the establishment of calibration methodologies and procedures. So once we finalize this feasibility, we would like to do a sea test, much closer than the stations, to check the procedure and the equipment. And after we have a confirmation from all these methods, softwares and equipment, we will do the calibration work in one of the hydroacoustic stations. H01 would be the one of the candidates because it's more accessible from land. So by saying that, I would like to thank you for listening, and if you would like to have some discussion on that, I will be here tomorrow and also during the rest of the SNT. So thanks.
Thank you. This is one of the more important issues at hand in the IMS sustainment, since the hydroacoustic is so very expensive.
Yeah.
So thanks for giving us this insight. Is there a quick question from anyone? Yep. Could you state your name, please?
Josephat Mullo from Kenya. Thank you very much for that insightful presentation. And if I got it right, the reason why you are now going to full chain in situ calibration is to get the condition of other equipment like the riser cable. So how will the full chain in situ calibration now give you information about the riser cable? Thank you.
Yeah, thank you for the question. Yes, that's correct. I mean, now only the electronics can be calibrated from the CRF, from the shore side. But with the in-situ calibration, we can have an opportunity to check the chain from the hydrophone until up to the electronics on the shore side. So that's the main profit of this exercise.
Thank you. Then we will refer the rest to the break after. Thank you so much.
Thank you.